If users have to rely on the outputs of complex machine learning models, they give up their agency over the automated process and are forced to trust models. We argue that the agency can be regained by interpreting an automated model as a team member that collaborates with a human, rather than dictates unexplainable predictions. This teamwork can be achieved by creating collaborative model-human interfaces. But how do we create such collaborative models? We developed an approach called Collaborative Semantic Inference, or CSI for short. CSI models introduce semantic hooks inside of models with which users can interact. Imagine a self-driving train that takes the decision to turn left or right at this intersection, but only exposes the prediction where it will end up. An interactive observation interface can thus only analyze where the train will end up. Consequently, once the train reaches the end of the track, an interface will not be able to show from where the train came. Now we introduce a hook in the model that resembles a lever at the first intersection that the self-driving train has to set as part of the prediction. A human can also set this lever. Immediately, a human can observe which turn the train is going to take and even control where the train is going. Similarly, once the train reaches the end of the track, all the human has to do is look at the position of the lever to know which track the train took. CSI describes a human and model collaboration technique that focuses on the three following aspects. User and model can collaborate in the decision process, users can interact with the semantically understandable model internals, and the system can use human and model reasoning to infer the desired output. CSI has a significant impact on the way visual interfaces and models are designed. In current observation approaches, the model design is seen as a static entity with which interfaces can interact. With CSI, the model design is no longer static. Instead, the design of the semantic interactions within the collaborative user-model process becomes the focus. We demonstrate the application of a CSI design process with a use case for document summarization. Imagine an end user called Anna who wants to use a summarization interface. Anna wants to summarize a news article about water on Mars. In the first step, to not start from a white paper, she asks the model to suggest a summary that can span the entire input, as shown by the blue highlights. That means that the model can suggest summarizing any part of the document that it thinks is relevant. During the forward step of the model, it infers 3 sentences which we present on the right. At the same time, the system also computes a backward step to show how the output summary covers the input. Since the input text can be longer than the browser window, we introduce a proxy element for each sentence in the input and output. The covered words in the input are presented with a red underline, and the proxies of the sentences with at least one covered word have a red border. In addition to the covered content, the interface visualizes the model attention, which means that it shows what input word the model focused on for each summary sentence. The attention is visualized using gray ribbons that are aggregated across each sentence and connect to proxy elements. By hovering over one of the sentences or proxies, Anna can highlight the relevant connections in yellow. Through these visual interactions with the output summary, Anna observes that the second input sentence splits into 2 different summary sentences. It is common for summarization models to compress, merge, and split input sentences, but the user would not be aware of where the inputs for each summary sentence originate. By exposing the internal model decisions in a CSI interface, a user can immediately discover how the input connects to the output. Anna believes that the summary should elaborate more on the already covered aspects from the input text. She now constrains the focus of the model to only the input that it already summarized. She matches the content selection with the blue highlights and the results of the backward model with the red underlines by clicking Match. After constraining the model hooks, she triggers the generation of an additional sentence. This new forward inference has an additional constraint on the model hooks and is conditioned on the already generated sentences. Anna dislikes the suggestion since it repeats information. To prevent the model from suggesting the same sentence again, she deselects the sentence from the input that had the highest influence on its generation by clicking on its proxy element. She then removes the suggested sentence from the summary. She generates another suggestion with this updated constraint. Influencing the reasoning process of the model in this way is only possible by the semantic interaction with the hook that is enabled by the CSI model. Next, Anna would like to include more details about water found on Mars. She starts writing "the water is" and then adds 3 dots that trigger sentence completion by the model. The resulting sentence is acceptable, but Anna spots an error with the verb is, which should actually be in past tense. She quickly corrects this output. To finalize the summary, Anna wants to write a sentence about parts of the input that are currently not included in the summary. She selects a previously not covered sentence in the input and requests a suggestion. She approves of the suggestion, but dislikes the repetition of "scientists say," which she quickly removes. To reflect on the whole summary, she looks at what the backward model predicts what was covered. By looking at the computed coverage, she can observe which sentences are covered and analyze how many of the proxies have a red border. Anna notices that her 6 summary sentences seem to cover the original text pretty well.
Yeah!
Thank you for watching. More details can be found in our paper.